This video is brought to you by mywayteaching.com.
In this part, let us study what is angular velocity and its relation with linear velocity. Okay. See, the linear velocity of the particle is related to the angular velocity. The relation between these two quantities involves a vector product that we learned in the previous sections. Okay. As we already studied that in rotational motion of a rigid body about a fixed axis, every particle of the body moves in a circle, isn't it? Similarly, you can consider here also rotation about a fixed axis here, okay, of a rigid body rotating about the fixed z axis moves in a circle with the center C. It is moving with the circle with center C. So whenever particles in when we consider the rotational motion of a rigid body, they move in a circle which lie in a plane perpendicular to the axis, and hence it has its center on this axis of rotation. You can see in here also, right? It is also showing a typical particle of the rigid body rotating about a fixed axis. The particle describes a circle with the center C on its axis. The radius of the circle is what? R, and the perpendicular distance of the point P from the axis. We also show the linear velocity vector v of the particle at point P. You can see here the linear velocity of the particle at point P. It is along the tangent at P to the circle, isn't it? See, let P dash, what you are seeing in this particular point, P dash be the position of the particle after an interval of time, that is delta t. Okay. The angle TCP dash, that is delta theta of the particle in time delta t, it describes the angular displacement. The average angular velocity of the particle over the time interval delta t is given by average angular velocity is given by delta theta by delta t, isn't it? Yes. So as delta t tends to 0, the ratio delta theta by delta t approaches a limit which is instantaneous angular velocity. Okay, as this delta t approaches 0, this delta theta by delta t will give d theta by dt. So that is called as instantaneous angular velocity, and we represent it by w. What is this? Instantaneous angular velocity. See, the magnitude of linear velocity v of a particle which is moving in a circle is related to the angular velocity of the particle w with a simple equation, that is v is equal to wr. We know this, isn't it? The linear velocity v is related to the angular velocity w with this very simple equation. So this equation, that is v is equal to wr, it applies to all the particles of a rigid body. For particles on the axis means if for those particles r will be equal to 0, isn't it? The the for the particles which lie exactly on this axis of rotation, r will be equal to 0, and in that particular case again v is equal to w into r will be also equal to 0. So the particles on the axis means the particles which lie on this axis, okay, are stationary. This verifies that the axis is fixed. So we use same angular velocity w for all the particles. So we therefore refer to w as the angular velocity of the whole body. Will not refer it as the angular velocity of a single particle. We will refer it as an angular velocity of the whole body. Okay. So we have characterized a pure translation of a body by all the parts of the body having the same velocity at any instant of time, isn't it? In case of pure translational motion, we studied that all the particles will be having same velocity at any instant of time. Similarly, in case of pure rotation by all the parts of the body, we can characterize it as having the same angular velocity at any instant of time. Okay, this characterization of rotation of a rigid body about a fixed axis is just another way of saying that each particle of the body moves in a circle. It is just as simple as that. It's just another way of telling that it moves in a circle which lies in a plane perpendicular to the axis and it has the center on the axis. So, in our discussion of all these angular velocity quantity, it seems like a scalar, isn't it? But it's not true. Angular velocity is not a scalar quantity, whereas it is an vector quantity. In fact, we shall accept it. We shall not justify this fact that angular velocity is a vector. We'll also accept it. For rotation about a fixed axis, the angular velocity vector lies along the axis of rotation and points out in the direction in which a right-handed screw would advance if the head of the screw is rotated with the body. You can see that here, if the head of the right-handed screw, okay, if the head of this right-handed screw, if it is rotated with the body, the screw advances in the direction of the angular velocity, isn't it? So if the sense of rotation of the body changes, so the does the direction. Here, moving in clockwise direction, the direction of angular velocity is like this. In anti-clockwise direction, here it is like this. Okay, with respect to that direction, the direction of angular velocity also changes. So the magnitude of this angular velocity w is equal to d theta by dt. See, in this case, the angular velocity vector w is directed along the fixed axis. You can see here, it is directed along the fixed axis. The linear velocity of the particle at point P is given by v cross w cross r. W cross r is the linear velocity of the particle. We know this formula, right? It is perpendicular to both W as well as R and it is directed along the tangent to the circle which is described by the particle. It is perpendicular to both W as well as R and it is directed along the tangent to the circle. So now let us see what is the vector product of W cross R corresponds to. See, in this figure, it shows that the vector W is directed along the fixed Z axis. And also the position vector R is equal to OP of the particle at P of the rigid body with respect to origin O. So here the origin is chosen to be on the axis of rotation, isn't it? So now if we consider W cross R, this R is given by OP. and we can write it as W cross OP can be represented using OC dot CP, isn't it? So we can write it as W cross OC plus W cross CP. But W and OC both lie in the same direction. Therefore, that W cross OC will become 0. Okay. So we will get W cross R is equal to W cross CP. Okay. So W cross R is a vector of magnitude WR and it is along the tangent to the circle which is described by the particle at P. The linear velocity vector V at point P has the same magnitude and direction. So we can write V is equal to W cross R. Okay. So this equation holds good even for rotation of a rigid body with one point fixed, such as the rotation of the top. In this case, R represents the position vector of the particle with respect to fixed point taken as origin. For rotation about a fixed axis, the direction of the vector W does not change. With time, its magnitude may, however, change from instant to instant. For the more general rotation, both the magnitude and the direction of W may change from instant to instant. See, in case of rotation of a fixed axis, the direction of the vector W will not change with time, but its magnitude it may change with the instant. From instant to instant its magnitude change. But if you consider the general rotation case, in that case both magnitude as well as direction both will change. Okay. So now let us study what is angular acceleration. Analogous to the kinetic variables of linear displacement and velocity v in translational motion. So, in case of translational motion, it is related with the quantities like linear displacement and linear velocity. In case of rotational motion, we have angular velocity and angular displacement. Okay. So, the concept of angular acceleration in analogy with linear acceleration defined as the time rate of change of velocity in translational motion. We define angular acceleration as the rate of change of angular velocity. Okay. We define angular acceleration as rate of change of angular velocity, that is nothing but dw by dt.